Sorry, there we go. Good, thank you. So, yeah, I presented to BASF about a month ago. I didn't know whether any of the same people were going to be in the presentation today, so this is a new deck. In fact, I'm very glad I didn't reuse the slide that Adrian, presented there. So this is pretty much all new material. We're mostly going to focus on complexity today. If you saw the previous presentation, I said, I think there's really two trends that both feed on each other. One of them is this idea that we've got seduced into, we call the application-centric quagmire. And that's what my previous presentation was mostly about, how application-centric thinking gets us and keeps us in the problem. But the other side of the coin is this complexity idea. And today we're mostly going to talk about, how much complexity do we really have? Why are we doing this to ourselves? How are we doing this to ourselves? And how can we get out? That's kind of today's theme. So there's a classic book. It was written in the 70s called The Mythical Man Month. It's still probably one of the best books ever written on the subject of software project management. Frederick Brooks wrote it based on his experience with the IBM 360 operating systems project, which was at the time probably one of the biggest software projects ever undertaken. By today's standards, it would be, opening stakes, but it was a big deal at the time. And then later, he wrote a very influential article. He didn't write this article. He wrote The Mythical Man Month in the 70s based on his experience in the 60s. And then he wrote this article in the 80s, by which time he was a professor. He was no longer actually in the business. It's called No Silver Bullet, Essence and Accidents of Software Engineering, where he puts forward the idea that there's two kinds of complexity in software: essential complexity, the complexity of the problem you're trying to solve, and accidental complexity. And he seemed to suggest that the accidental complexity was a small proportion, and therefore any attempts to speed up software development were only going to affect the small bit of this. And as we're going to see, the world kind of moved on since then. He wrote that article in the 80s when the Moore's Law was really kicking in, and it was totally obvious. The mid 80s there, everyone in software was jealous of year-over-year improvements in hardware. And this is a log scale, obviously. This is very exponentially bent way up. And at the time he wrote, or the project he wrote his first book about, was about computer systems that essentially processed punched cards. So they were not very complex. Most payroll transactions could fit in a single 80-column card. So we didn't have the kind of complexity we currently have. And maybe he was right, that the accidental complexity in a system like that perhaps was a small percentage. But we're gonna run the tape forward a little bit and see what really happened. The other thing that was going on in people's minds was, gee, every time in manufacturing, every time we double the amount of our production, the unit cost goes down. It's called the experience curve or the learning curve or whatever you want to call it. And it's a relatively constant improvement because, when you're making a lot of the same things that don't interact with each other, you learn a little bit, and the millionth, shampoo bottle or whatever this is knows nothing about the 999,000th one and isn't affected by that, where software is just the opposite. The millionth line of code or the millionth column heading has to deal with all the other ones that preceded it. And every time you add on, it gets worse instead of getting better. And I think, mentally we weren't prepared for that because we're used to this idea of economy of scale, and as things get bigger, they get better and cheaper and all that. So that's what we're going to talk about today. We're going to talk about complexity. We're going to talk about where did it come from, what's it cost you, what's the hidden, there's a very big hidden tax here, and then what you can do about it. So that's pretty much it today. Deloitte did a study of different industries, how much they spend on IT. Manufacturing, presumably chemical manufacturing is down there toward the bottom, but even at 2% of revenue, if you took BASF's revenue multiplied by 2%, you would estimate that you're probably spending $1.5 billion or so on IT every year. Question is that money well spent? Forrester, another consulting firm, looked at the worldwide IT marketplace and where does the money go? Well, a lot of it from about noon, 12 o'clock to 2:30 over there, the lightest blue is equipment. Probably not going to affect that much. Down there near 5 and 6 o'clock, communication equipment, okay, probably not going to affect that too much, or even some of the outsourcing, from 7 o'clock to about 9 o'clock on the dial there. But the two bits, the upper left and the lower right, account for about 37% of what people spend on information systems. Consulting, systems integration, a huge piece. Middleware, which is software that's just there to try and solve the problems that the other software created. Custom software applications, etc. It's a big chunk of spend. If I was right on the previous slide, and if Forrester's right here, you're spending somewhere in the neighborhood of $500 million a year, just in those couple of categories. And those happen to be the categories most affected by reducing complexity, software, data-centric, all that kind of stuff. So what do you get for $500 million a year in applications and integration and all that kind of stuff? Well, at some point, because we're adding more, we're rarely simplifying or taking away. We're almost always putting more in, and every additional thing you add has to deal with everything that came before it if you don't get rid of anything. And there is a point at which no one will be able to understand the thing that's been created. And someone called this the complexity barrier, but at some point things will just freeze up. It becomes so complicated. And I'm going to suggest we're already there. We were at a client recently, did a project for them, and in parallel with our project, they did a data profiling exercise. And the data profiling exercise found that they had 70 million bits of metadata, 70 million columns, if you will, under management. So if they had about 3,000 applications and all kinds of data sets and things all over the place. And this is a company not as big as BASF. I'm going to guess that if you did a similar study, you'd find something similar. And I pointed out, so this is 70 million fields or columns or attributes, whatever you want to call them. Those are all different concepts. It's not like 70 million, detergent bottles or whatever those things were on that one slide. These are 70 million things that have to know about each other and interact and copy from one to another and show up in a form. And humans have to understand many of them. And, as I pointed out to them, humans can learn about 5,000 new things a year. That's when you're going to college and young and really learning. It would take you 14,000 years to understand just the metadata here. They also found, which was very untoward, that in that 70 million, there were 8,397 columns that had social security numbers. That's a tax ID here in the U.S. that's very sensitive. Every time there's a data security leak, people worry about whether social security numbers were leaked, because that's a big deal. So they have 8,300 places in their datascape that they have this kind of information. You know, not 8,300 rows, 8,300 unique columns somewhere. And we pointed out to them in the model we had developed for them, and where going forward, there was one place to put Social Security number, and there only ever would be one place, because it was attached, it was an ID of a person, came from the Social Security Administration. And no matter what, whether you were an employee or a customer or a beneficiary or had life insurance or all the various things that caused them to have Social Security numbers in their system, in the future system, there'd be one. So I mean, right there, there's an 8,300 to 1 reduction in complexity possible. So, you know, they've got 3,000 major multi-user applications, and every time, you guys probably know this, every time you change one, the whole rest of the structure is affected. Oh my God, if I take that out, what else is going to collapse? So the question is, so that's true. What are you going to do about that? Well, our proposal, our recipe, our suggestion is to become data-centric, and that which is a process. It's not a product. It's not an application for sure. And it's certainly not binary. You don't suddenly wake up one day and say, I am data-centric. But you can tell that you're becoming more data-centric to the extent that the functionality that exists in your enterprise is loosely bound, meaning it could easily be replaced and substituted in and out without breaking anything else. That's what loosely bound means. And the controversial part of this is the next 4 words: a single, simple, extensible, federatable, shared model. I guess it's 5 words. Every place we've gone, no matter how complex or how large the enterprise, there is a single model that's fairly simple. When we say fairly simple, 500 or 600 concepts that cover most of the things you find in all those thousands of applications. Not every single small distinction, but the big things that stick it together, and then you can by extending it, that's what the extensible bit is, add in the other fine-grained distinctions. And federatable means you don't have to put it all in one place. It's not like a data warehouse where everything has to co-reside in order to get any value. You can leave things where they are, query them as needed, or you can move them together for performance reasons. It's a very adjustable thing as you go along, and that it needs to be shared by all the people that participate in it. And it's the application-centric mindset that says, no, I don't want to share. Sharing is hard. I'd rather just solve my problem by myself and stay in my lane. So we say there's 3 legs to the 3-legged stool here of becoming data-centric. We've observed a lot of people doing this. It is possible to do this without semantics or graph databases or model-driven, but that's the hard way. One of a sister division of one of our clients. So we work with Standard & Poor's and Platts, which is one division of Standard & Poor's, but what they call market intelligence became data-centric, and they genuinely are the hard way. They do it with relational technology and huge amount of work, but it is possible. But this is the easier way to do it. So a graph database is I'll have just a couple slides on this, and these are repeats from the last time if you saw this, but sometimes some of these things bear repeating. Gives you 3 things. It gives you flexibility, it gives you integration almost for free, and this is how you start getting rid of your data silos. So how does it work? On the right is a table, like in a traditional information system, where in this case we have information about James Bond and the much lesser known Andy Renton. We can convert any data that we can find in a relational database, or frankly in unstructured data or semi-structured like XML or JSON or HTML. Any information can be reduced to this one simple pattern, which is 2 nodes connected by an edge. In this case, the one node, 007, represents this secret agent. The other node just represents his name at this point. We're going to have some more clever things in a minute. And the edge just says, what is it that connects these 2? So that thing's called a digraph or a directed graph. That's why these things are called graph databases. It's not because of the graphics, it's because of this arrangement of nodes and edges. How it gets its flexibility in a relational database, if you don't have columns for information, you can't store the information. So you have to go talk to the DBA, add another column, all that kind of stuff. Here, anytime you discover new information from any other system or any other source, it just attaches into the graph database here. In this case, somewhere we find out that 007 was assigned this particular Rolex watch. We later find that that is the watch that contains the garrote, for taking people's necks off. And just did this to show that this graph, you can keep extending it. You've seen lots of pictures of these very complex graphical structures. This is essentially where they come from. Whoops, I left out the integration almost for free, is this little colon I have in front of all the names inside the ovals and the names on the edges is actually a PowerPoint shorthand, because I couldn't fit the whole thing. It would look terrible, but that shorthand represents a namespace, and in best practice that's owned by someone like BASF would have their own, they own BASF.com, therefore you can mint identifiers in your domain name and be quite confident that they're unique in the world, they're globally unique. And what's interesting about that, at first it doesn't sound like that big of a deal, but if you have globally unique identifiers, then you don't need any metadata to connect things. Because once this is, in this case, I usually say it's Her Majesty's Secret Service.co.uk/agents/007, once you know that, no matter where you find that information, in a document, in a dossier, in a database, it always represents the same thing, and therefore the information snaps together. And that's why we say you can get integration almost for free. You're not writing joins and ETLs and all that kind of stuff. The second leg is semantics, which is the study of meaning. This is where the simplicity part comes from. So the graph gives you flexibility, semantics gives you simplicity, and as we'll see in a minute, the model gives you reduction code, which is also very helpful. So it is possible to use semantics inappropriately and build semantic silos, but our contention is if you use a small, well-vetted upper ontology, build out your own enterprise ontology and keep it elegant, it has two benefits. You can really reduce the complexity of the model, and I'll have a couple of examples in a minute, and makes it easier to integrate with other systems that were similarly built. So here's an example. This actually turned out was Schneider Electric's. They have they sell electric products. They sell about 1 million different electric products. That information was in a product catalog. This is only a small portion of that product catalog, because obviously at some point it won't fit on a slide. This catalog had 700 tables and 7,000 attributes. So the way we count, we say there's 7,700 concepts you would need to understand to kind of master that particular bunch of data. Those tables and attributes, what was stored in them were 1 million products and all their product characteristics and all the marketing information and the prices and the countries they were sold in. And, there is a lot there to be sure, but we designed an enterprise ontology for them, and then we populated it with the data from this database. And after we had done it, we weren't really thinking of it at the time, but afterward we wrote a query, and found out that we'd only populated 46 classes and 36 properties. Now, properties are reusable in semantics, which, obviously they're not in relational. It may seem odd that there are fewer properties than classes, but that's the way this happens a lot of the time. So there's 82 concepts you would need to understand to master the complexity of their 1 million products. So that is almost 100-fold reduction in complexity just in one system. And our contention is the more systems you bring in, the more the complexity is reduced. They had acquired another company that had its own product catalog. It wasn't as complex as this, but it had a couple of thousand, I think it was just over 1,000, 1,500 concepts. They only did residential, light switches and stuff like that. But it was, 1,500 or so concepts that were completely different. They're structurally, naming, everything, level of abstraction different than this. But yet once you have the simple model, you can acquire the data from the other system, and we added 2 or 3 new attributes. So the simplicity really pays off. And you would think you'd lose functionality when you simplify things, but actually you increase functionality. We've found much better ways to do product configuration, because you could actually understand what all the characteristics of these electrical products were and what they meant, because they weren't hidden in all this structure. We worked with a company that sells data for a living, and their problem was they have thousands of what they call data products, which are either APIs or data sets, the things you can subscribe to, and each one has hundreds or thousands of attributes. They did an inventory and they found out they have 150,000 different attributes available for sale, and they're continually trying to move customers from one product to another, but it's so complicated, very hard to do it. They're missing their revenue targets, etc. So we built them an enterprise ontology that had far less than 500 concepts that covered pretty much everything they had for sale here. It really wasn't that complex. It was not 150,000 unique things. I have some other presentations to give you a sense for what constituted a unique attribute that you could easily cover with a simple model. But they had to, you really can't map 150,000 things directly to 500. It's too much of a fan in. It doesn't do you any good. So we built this thing in the middle, which was helped them identify what these things really meant, so they could help move customers from one product to another. But anyhow, that's another example of a 300-fold reduction in complexity. So, it's certainly possible and desirable, I would suggest. The other thing semantics buys you is the ability to do what's called inference, find new knowledge from existing knowledge. And one of the things that's pretty cool about it that a lot of other rule or even machine learning environments don't provide is, once you learn something, you just express it as another triple, put it back in the knowledge graph, and it's available for everyone else. This little example here is we have something similar to GDPR, and of course it takes a bit of inference to figure out whether a particular field or action or whatever is covered by a particular regulation. And then the last leg of the 3-legged stool, we call it model-driven everything. The observation is, you look at these giant complex systems, and if you stare at them long enough, as I have, you see that most of them are just forms and tables and graphs, a few simple things just done over and over and over again. And the only thing that's different is, what concepts is it displaying, what order, what validation, what constraints. But all of that can be, you could either describe it in a model and parametrically execute it, or you can write code, which is what people have been doing for decades. But that code is expensive to write, expensive to test, very expensive to maintain. When you have, when I said these people have 70 million columns under management, on average, anytime you add another attribute to a system, this is average, but it's not that far off, you add about 1,500 more lines of code, which is by extension another 15 bugs. Every column introduces another 15 bugs that are latent. You haven't found them yet, but they're out there. Every study that's ever been done, even with a NASA level clean room, there are latent bugs in software. So if we can reduce the amount of software we have to build, correspondingly we reduce cost and bugs. So if you decide you want to become data centric, you really need 2 things. This thing on the right here is a artist's rendition of an architecture that's data-centric. So in the center, those little, we call them the grapefruit pieces, are different repositories of data. So if you're going to be data-centric, you should have data at the center of your architecture. And each of those layers working out, I'm not going to go into it today because I want to leave some time for the questions. Each of those layers is some capability that the architecture needs to have that historically we had in our application systems. These are things like federation, being able to get data from multiple databases and combine it, constraint management, making sure that all the data that's in the database adheres to certain rules. It's identity management, it's authorization, making sure that people can only see what they need to see, things like that. So that's, and at the moment, you can't really buy that off the shelf. Most of our clients are building what they need from technology that exists. So that's, and I'll have a couple slides, in the next couple slides, go into a little bit more detail how you grow that essentially. The other side is you need an approach. And the approach that we take, we call it think big and start small. Everyone wants to start small these days, and it's not a bad strategy. You know, agile and everything is about starting small, but you run a risk starting small with this stuff that you will just build another silo. Or sometimes you start too small. You know, proofs of concepts rarely go anywhere. So if you start too small with that kind of stuff, it just dies out. But even a decent sized project runs the danger of becoming another silo. So the think big part of the approach says do at least enough of the enterprise modeling that you're confident when you do this first project, it will fit in and be future-proof such that as you extend to other subdomains, it all kind of fits into a coherent, bigger picture. So this architecture, we've been observing it now, kind of grows as these chevrons indicate. Initially, in the green there, people just set up a sandbox, get the thing designed, move some data in, just to make sure it really works before you've made too much commitment. But in that process, it's partly, bringing stakeholders in when they see their own data there at the requisite level of detail, and they recognize things, they can see things they hadn't seen before. They start to buy in and understand and accept that. But the other thing that's happening is that's where you're building the model and making sure it's complete and thorough and has enough detail. In the blue kind of areas where people start moving it into production, using it kind of like a data warehouse. And I have a couple slides because some of the questions that came up for today's talk, I think, are pretty much focused in this blue area here. Then people get to this point where they go, wait a minute, if I have all my data here expressed in this simple, flexible way, unlike a data warehouse where you're kind of stuck. You can bring all the data together and you can report on it, but you can't build new functionality in a data warehouse or even a data lake. You rely on the legacy systems to feed you data. But here, in this orange chevron, you look at this and say, aha, I can just write code, ACID code, transactional update code directly against this graph database and build at least some application functionality. And a lot of our clients are pretty much in that chevron right now. The last two are about model driven, and at first it's build a way to at least build the simple parts of an application so you can get a lot of productivity and a lot of speed. But when you finally get to where you can build something very sophisticated, then and very few people are there. We know of a couple. None of our clients are there yet, but we're working on it. You get to that point, and all of a sudden you go, wait a minute. You have enough confidence to say, I could build almost anything in this environment. So here's a simpler way of thinking about that same thing. You get a different capability at each stage. So the enterprise gets a capability. One capability is the enterprise knows that simplification is possible. Then you have a better warehouse. You start work on the next generation. You can build at least part of your app rapidly, at least the simple ones. And then finally, your capability is some alternative to your legacy systems. What's really happening, though, is the enterprise develops this capability, and the value is as you roll it out. So any large enterprise has lots of divisions. You're going to start in one division. Some other division is going to say, oh, we like that. We want to do that. Start rolling it out. The enterprise kind of moves on. You start rolling it out. So that's kind of what a long-term plan looks like. Every step along the way is relatively economically conservative. These aren't $100 million big bang ERP projects. These are, small, several hundred thousand, less than $1 million, almost any of these. You guys had asked about where do things like data science, graph analytics, ML, machine learning, all that stuff fit in. It's mostly in the second phase here when you have enough of the data understood, harmonized in the graph database. It's a huge win for data scientists because, as you know, data scientists spend something like 70% of their time just wrangling data, finding out the source, conforming it, figuring out what it means, improving the quality of it if necessary. A lot of that can be outsourced, if you will, to the graph. And the same with people doing machine learning, that they need access to good, clean data to get started rather than spending all their time, looking for that. What we're kind of suggesting, if you take a big picture, long-term thing, we've got, as I was suggesting earlier, your IT business as usual is spending a fair chunk of money. Actually, that would probably be growing over time. We're suggesting, setting aside a small amount of money to run something in parallel. You have to keep, for the next several years, like it or not, you're going to keep implementing what I call Neolegacy Systems, the next generation. You have to replace some aging system with some slightly less aging system. We know that's going to continue on. But the hope is that what you learn in the data-centric journey begins to start paying off in the IT business as usual, and it's going to show off in two places, or show off, I guess, in two places. One is just pure cost savings. You're going to start dropping the cost of integration. That's going to be the first thing that's going to drop, and then replacement legacy systems and maintenance on some of these things and licensing for some of these things. And it's just over time going to start going down, and then you get cost reduction for new stuff like big data and machine learning. So that's the rough idea there. This all sounds quite out there and far-fetched. I love this little cartoon. What we need is a brand new idea that's been thoroughly tested. Well, that's what this is. There's still, I would say, less than 1% of all companies have adopted this, and yet it is thoroughly tested. These are our clients. They're all using it. In fact, between the last, I don't know how to advance. Between the last time we spoke to BASF and today, we signed DuPont as a client. So that's somebody right there in your industry. But a lot of big mainstream companies are doing this or are on the journey. There's a bunch more companies whose names you wouldn't recognize. I could have another slide with a bunch of others. And then there's some people whose names you would recognize. These aren't our clients, but they have also leveraged this approach to some pretty fantastic, God, this thing's advancing on its own, in some pretty fantastic ways. Google, the Google Knowledge Graph was an RDF knowledge graph that they acquired about 4 or 5 years ago. And if you notice, 4 or 5 years ago, when you searched in Google, you got references via keywords to documents. That's essentially now you get answers to questions, and you get these little sidebars, the little knowledge cards. It has changed quite a bit behind the scenes, and it's pretty much based on their knowledge graph. Facebook is a graph. That's where all the power and the recommendations and all this stuff comes in, as is LinkedIn. In fact, both of them at one point or another had user APIs to allow you to the graph. They don't anymore. They got in a lot of trouble because, electioneering and all that kind of stuff. One of my favorites that we've been tracking a lot is a hospital called Montefiore. They have really done what every other hospital wants to do and have been stymied, and they use this exact approach. We haven't been involved with them yet. They're going to license this technology, and hopefully we're going to take it to other healthcare institutions. We've had a lot of conversations with them. Thomson Reuters has gone a long way in building and making publicly available, and Amazon's recommendation engine, product knowledge graph is all based on this kind of technology.
Thank you much for your talk so far. My name's Tobias. I work as a data engineer / data scientist at EC Codings. And one question that I wanted to ask you, also looking at the Schneider Electric study, what is the typical duration of such a project on your side, meaning from maybe even up to implementation of the solution that you've come up with? Yeah, I'm just wondering, in general, either or specifically on the Schneider Electric use case.
Yeah, we typically try and chunk our projects into 3 to 6 month chunks, and 2 to 3 ontologists from our side, joined by some folks from your side. And the reason, that's just what people don't want to risk a huge amount. They want to see some results in a reasonable amount of time. And typically there are follow-ons. So in the case of Schneider, there was, it's been a while now, I think it was about 3 months to get the original ontology and a little bit of data test loaded, which convinced them that this would work. We then had another phase where we partnered with a different company who built out the user interface. And in parallel, we were participating in that, is when we figured out that we could do a different approach to configuration management. We'd originally tried something in the first phase that didn't work. That was kind of disappointing, but luckily we got to come back, tried something else that actually did work. So I think, and if I remember correctly, I think there was a third phase. Well, there's certainly that phase where we integrated the company that they acquired in Australia. So there's probably 3 phases, maybe spread out over a year, something like that. I see a couple of hands.
Yes, there is a question from Thomas Kruger. Thomas, please.
Yeah, hello. My name is Thomas. Hello, Dave. Thank you very much for your very interesting speech. I'm a chemist by education. I'm interested in, let's say, improving data use in our R&D community. So a lot what you said resonates with me, even though I didn't understand all of it. I have to admit, a lot of information, but it sounds very logical, very much. You say we need to spend only 0.25% to get started. So I have 2 questions. Why is not more companies jumping on it? What's the problem? And the second, what would be the concrete first steps that you would recommend? Maybe you come later to that, and I postpone my question.
Well, no, I'll take a shot at it now, and then we can keep elaborating.
Yeah.
I think there's several reasons that not more companies have jumped on this bandwagon, and Adrian kind of hinted at them from my previous presentation. One is that up to now, IT direction in most large enterprises, unfortunately, has mostly been driven by vendors. And it's gone through a couple of different cycles. For quite a while, we got the idea that you had to go out and buy application packages. So pretty soon the application vendors were essentially writing the script for what was going to happen next. It actually got worse in the early 2000s when people were outsourcing their systems. So they were sort of doubly removed from the ability to improve them. So now you've got an outsourced vendor using application software. So those 2 things are both dictating what you're going to do. And you've got perverse incentives in there. Systems integrators, application software providers, all those folks actually make a lot of money by having this thing be very complex. So they're They're incredibly incented to keep this party going. So that's kind of that's all the bad news, and I've got all kinds of examples and case studies of, you know, things that are very publicly well known that have cost, you know, thousands of times more than they should. The good news, and where I see some rays of light, this movement that's going on right now, it's called digital transformation. It's a bit of a misnomer, and B, fails more often than it succeeds, but it's still hopeful, and and the whole digital transformation thing, if you haven't been keeping up on that buzzword, you know, is mostly about changing the customer's experience by making their interaction more completely digital and removing the need for them to actually know and understand your complex back-end systems. Well, given all that, the good news is control of a lot of the IT budget has moved out of IT and into the line of business, where they actually care about this stuff. So that's where I think the hope is. And your question is where to get started. You know, what we've found, we can start almost anywhere. You have to have a reasonable business case, because if you do something, you want at the end for people to say, oh yeah, I get it, that actually saved money, that did something, and then on you go. I don't think your mic's on.
Yeah, right. Sorry. So the first step is a business case, and this is easy to be done. So we can quickly find the benefits to convince, let's say, upper management to do this.
You know, we can help you, but here's what to look for. If there's some problem area where currently you can get answers, but either it becomes a small research project, and by a small research project I mean hours to days. You know, you say, oh, we need to know this. Okay, Susie has to go look in this system, and Billy has to look in that system, and somebody builds a spreadsheet and they put it together and say, ta-da, there's the answer. If you say, you know, I have an intuition that if we harmonize that data, I could just run a query and find that answer. So if you can think about something that sort of looks like that, that's generally a good starting point. And it doesn't have to be huge and complex. You know, you don't have to boil the ocean. You just have to get data from 2 or 3 sources that you previously, you know, would go research. And in some cases, some of the ones we've done, in some cases, one of those sources might be unstructured. You might literally have documents, read, extract, combine with structured.
Okay. Thank you very much.
Yeah, you bet.
Any other question that you would like to ask to Dave?
I'm trying to remember what I did have a few more slides, and somehow in the act of saving it, I ditched them, but oh well. And now I don't remember what they were. Matthew has his hand up.
Yeah, thank you. So first of all, thank you very much for this very nice overview and presentation. So I am working on the architecture of the bioscience environment at BASF. And I have one specific question. So you mentioned at the very beginning of your talk about that the graph can help to reduce the complexity when it comes up to product or business concepts. My question would be in respect to the simplification, basically to the legacy application landscape, because it's one thing to simplify the consumption of the content, but I would be interested as well to understand how this can help to simplify the landscape at all.
Right. So the landscape doesn't get simplified until you can replace it. You know, and at first you may think, oh, that's too big of an ask. I don't want to go there. It's too much. What you really want to do is get yourself in the position where you'd feel confident, maybe initially just peeling away little pieces of the legacy infrastructure. So we talked to this one company. We haven't gotten to work with them yet. They had a big ERP system, an SAP system, and they wanted to add some new functionality onto it. I think it was material returns. You know, it's always a classic. It's I don't know, you guys probably don't deal with returns much in the chemical business, but everybody else does. And it would be many millions of dollars to add that onto an existing ERP system. It's big and complex knowledge. And the point we were trying to make with them, they haven't bought yet, but is you can take a lot of the data you have in your ERP system, put it in the graph, and then do the material returns functionality directly on the graph. And so instead of adding to the legacy, at least you're not making it worse. But then over time, you start looking at some of the other functions that are in your legacy system and say, oh, wait a minute, it's doing the tool crib. Maybe that's not the easiest way to do the tool crib. Let's do the tool crib in the graph, and just piece by piece, just start taking things out until you say, wow, maybe I don't need those legacy systems.
So, yeah, okay, thank you. Maybe another question in this respect. Sure. Beside the ontologies that are needed to build up your graph as well, when we talk about the terms, how would you balance that compared to classical data catalog activities? Because in my opinion, the data catalog would be exactly the tool to analyze the lineage and the consolidation of the source systems, while the ontology is much more about the consumption. So maybe you can speak about that?
Sure. You might have guessed, but the answer I'm going to come up with is, turns out there is an ontology of data catalogs. In fact, it's publicly available. It's out there. The W3C standardized. It's called DCAT for data catalog, I guess is what it stands for. And the idea is exactly what you're suggesting. You know, for most people, they have data catalogs because of the vast number of data sets they have. You know, they have lots and lots of time series and various other things, and it's too much for a human to know which one, you know, to get. We doing a little bit of work with the International Monetary Fund, and they do work with Federal Reserve Bank, and the Federal Reserve Bank has 400,000 data sets they make publicly available. Well, that's a lot to keep track of. You do need a catalog, as you suggest. The interesting thing I think about having an ontology as your catalog is now you have a hope for connecting your legacy systems to your data sets. In fact, some of your data sets came from your legacy systems. You know, some of them you got from the public, and some of them you leased and rented and all this, and you put it all together. But really, it's kind of interesting to know, oh, this data set is an extract from the employee master table. And just as you said, you know, lineage is key. There's an interesting thing you can do with a knowledge graph that's harder to do with data catalogs, I think, a non-ontology data catalog. In a regular data catalog, you mostly talk about lineage at the meta level, at the process level. I know that this data set came from this data set and it went through this program. It's actually possible, we haven't done it yet with any of our clients, so we've kind of done experiments on this, to know at the individual triple level, where did this triple come from? Because by the time you've consolidated a whole bunch of data sets and cleaned them up and augmented them, you think they all came through one process, but they really didn't. Every single piece of data was either fabricated in the process or came from the employee master file, or came from Dun & Bradstreet, or came from whoever you get data from. So it's kind of there's some interesting possibilities in there.
Thank you very much.
Yeah, you bet. We're getting some more hands now. That's good. Thomas or Peter, one of you guys want to go?
Yeah, then Peter, go first. I already asked one question. Sorry for asking again. So just maybe it's a misunderstanding, but I thought I was very interested in really, let's say, addressing the big cake that you have shown in one of your first slides, the 500 million estimated costs that BASF would spend on those data system integration, all the applications. This would really be the huge savings. If I got you right now with your answer to Matthew's question, we would really everything would be kept. Maybe it's a misunderstanding, and the savings that we would generate would come only from the benefits from each individual case and connection of data that we generate. But the big thing would still remain. Is that well understood?
I mean, this is a long-term journey. So for the first couple of years, you should assume that most of your legacy environment, and therefore most of your legacy spending, is going to stay more or less as it is. Mm-hmm. Maybe probably the best news is maybe we can prevent some big unnecessary project. You know, hopefully you can stall something out. But at some point, 2 or 3 years in, you start saying, aha, you know that project I was going to do, the $10 million project, I now have enough infrastructure in place to do the same thing for 200,000. And you start whittling away at that until eventually you say, wait a minute, that legacy system, I've already replicated half of its functionality. Let's go after the other half. And when I get rid of it, the licensing goes away, the maintenance goes away, the systems integration for it goes away, you know, but it's not going to happen overnight. This is going to, you know, at least 5 years, probably 10 years to really make some progress on that.
Okay, good. Yeah, thanks for the clarification.
And if some of you guys saw the Amgen presentation, we're now working with Amgen. We weren't at the time he gave that presentation, but one of the great lines in there was he said, you have to arrange this so it's a self-funding journey. I think it's a very profound insight. You don't want to make this a big high-risk thing. You want to make it a lot of little things that fund themselves as they go, but everything gets better over time.
Thank you very much.
Yeah. Peter,
okay, coming up with my question. Can you hear me now?
Yeah.
Okay. Peter Hoffmann. I'm working in Thomas Group. I'm responsible for the digitalization of the research and development labs. Mm-hmm. And we are currently working on an ontology which has a certain focus. It's few small ontologies. Mm-hmm. We saw already it's not one ontology possible, and we try to get usage of legacy data, that means data existing in SAP, mm-hmm. connect them with an ontology and get a user interface at the end where the data can be consumed, and also something to maintain the data, add new data in a very easy way. We see mm-hmm. that using like Web Protégé, something like that, is really mm-hmm. challenging for people not knowing yes. what's behind, and they can make a lot of mistakes. What is your opinion about the governance of the relations? Because ontologies in general, it's nothing than a meaningful link to an information.
Yep. Wow, that's excellent. First, let me tell you, you just validated everything I said, because what you just described you did is what I'm suggesting people should do. You know, build an ontology, extract data from a legacy system, put it in a triple store, create a user interface. You know, so if anybody else on the call wants to know that this is possible and I'm not smoking dope, go talk to Peter. But now let me answer your governance question. What we're finding is that, well, in the first place, if you step way back and you realize why governance is so hard now. So, you know, that insurance company we talked about, it had 70 million columns. They're attempting to govern that. And they have armies of what they call data stewards who are, you know, constantly, you know, talking to people and trying to figure out, can we change this? Should we change this? So we're trying to change the whole equation and the economics to say the ontology itself is going to have just a few hundred concepts. And you only need a small number of people to govern that, you know, some ontologists. Each extension will typically add a few, maybe a few dozen classes. Most of the extensions are taxonomic distinctions. And typically in most businesses, there's a separate governance process for taxonomies. The good news is, you know, mere mortals can do taxonomy. You know, it's an indented list and they argue about them a lot, but they say, okay, let's have 10 types of whatever it is, chemical substance or something. So they get together and convince themselves that it's right. And if the ontology is designed well, changing some taxonomic distinctions will not break anything. And that's how you can separate the governance. There's a lot of people who've made gigantic ontologies. I don't know if you guys deal with the medical domain or SNOMED, but SNOMED has 300,000 classes in an ontology. Well, they have a huge governance problem. That hospital I talked about, Montefiore, took in all of SNOMED, but took it in as instances, and they manage it as a taxonomy instead of trying to manage it as an ontology. And it's way easier to govern and manage. So there's, things like, you just look at the numerical complexity and the side effect and say, how am I going to govern this?
That means we should really care about in the very beginning to have an ontology which is really extendable.
Yep.
Think big, yeah,
Yep.
extended possibility, and not to make too much of hurdles in the very beginning.
Exactly. Yep. And we have a free starting point. We call it GIST. It's on our website. We call it the Minimalist Upper Ontology for Business. And it's kind of the product of us we've probably done 50 projects now in the last 5 years. And we always use GIST as a starting point, and we keep folding what we learn back into GIST so that there's very few ambiguities, that we're trying to avoid the rookie mistakes. It's a pretty good place to start. It has nothing about chemistry or any of that, but at least it hangs together all the, your employees and your customers and suppliers and all that stuff.
Okay, thank you.
Yeah. So we're at the hour here, but I'm